Section 8, Functional Coverage. One of the key reasons for using SystemVerilog to write OOP Testbench code is its extensive support for functional coverage metrics. Functional coverage gives us an idea how thorough our testbench code is in exercising all of the functionality of our design under test. In the case of our filter, we'd like to be sure that the full frequency range is adequately covered from 10 to 120 kilohertz. We want to be sure that the applied frequencies don't cluster around the middle. We want to be sure that all modes are covered. And we'd like to know that mode 7 doesn't just occur at the higher frequency end of the spectrum. Functional coverage metrics answer all these questions, and any gaps in the coverage could possibly conceal hidden design flaws. So let's start with coverage for just our frequency input. We define a cover group named in this example CVG. In a typical UVM test bench, this might reside inside a dedicated class called coverage. But it's simpler in our case to just embed it within the monitor class. There it has direct access to properties of interest like the random frequency, the mode, and so on. And also the monitor understands the timing of the DUT and allows us to sample statistics at the right time in the clock cycle. That happens when we call the built-in sample method on our cover group object CVG. We define a cover point to tell the simulator that we want metrics on the frequency, and we've arbitrarily divided the frequency range into half a dozen bins. To reach 100% coverage of frequency, every bin has to be filled at least once. And so we've now got the frequency covered. Let's see the results. Every simulator, once it sees a cover group, will begin compiling coverage metrics. The detailed mechanics are simulator specific. Here we're looking at VCS. The statistics are collected within a Linux directory called simv.vdb, and we can use the utility URG, Unified Report Generator, to analyze the statistics and display them in HTML format. And here we see that we've got 100% coverage in just 20 trials. We filled all 6 bins. For example, bin B80 had 3 hits. And all this was extracted from the Unified Coverage Report. Let's extend our code to handle the full-blown test case that we described in section 6. At some point, the DUT will go into power down mode. We don't want to gather frequency statistics during those states. So here we're adding an if and only if clause to limit the collection of coverage statistics to the filter or the resume state, ignoring bypass and wait. And so we can freely use all the SystemVerilog syntax for functional coverage in the language. Now let's cover the mode. A group can encompass several items, so we have added another cover point for the mode. We're naming this mode underscore CVG, and we've added an if and only if clause to it as well. In addition, we not only want to cover the individual frequencies in the individual modes, but also their Cartesian product. Every possible pairing of an enumerated mode and a frequency bin. That has a total of 6 times 8 or 48 bins that we need to fill. Here's the results of a run. We've gone to 40 trials in this simulation run, And as we see, we easily met 100% coverage of the 6 frequency bins individually, and likewise all 8 modes, but our cross coverage is only 65%. Why so low? Well, it's because the modes and frequencies are uniformly distributed. So the probability of hitting any one pairing of mode and frequency bin is only 1 out of 48, barely 2%. And so we've got quite a few gaps left in the coverage map. And we can try a couple of different tactics to reach 100%. Let's look at the more elegant possibility first. We'll just try various SystemVerilog tactics to try to improve the coverage. Here we're employing an inline constraint, a so-called width constraint. We've tacked this on to the code where we call the randomize method within the body task of the sequence. And this occurs during the tail of our test case after we've resumed filtering operation after the power down mode. And the idea is we'd like to single out these 3 empty bins and force coverage of these 3. So we're forcing the mode to M0 and asking for frequencies inside the range of 20 to 79 kilohertz. This in general can be a very powerful tactic, but in this case it fails. The reason is, as Dave Rich pointed out in his paper SystemVerilog Constraints, constraints can conflict, especially when they're called from multiple objects. So what's happening here is we've used this unnamed width constraint to force the mode to M0, forgetting that we've already got a static queue of used values filling up. And in this simulation run, mode 0 was already used, and so the constraint preventing us from using it again conflicts with the width constraint. We get a fatal runtime error. Let's drop back and employ a more brute force approach. We'll simply increase the number of trials until we see 100%. So as you can see, each blue square here represents a separate simulation run. This one is 56 trials, and we're increasing the coverage almost linearly, but above 90%, it begins to level off. The reason being, as stated previously, the probability of filling one of those pink bins is only 2%. So it actually takes us quite a while, 176 trials, to reach 100%. Because of XModel's speed in testing even a transistor-based DUT, this is no problem. We ran the simulation in less than a minute, 41 seconds. And so one of the advantages of XModel is that we can run hundreds, even thousands of iterations on an analog DUT to increase functional coverage. To summarize, verification teams can use this approach to assure thorough coverage of all the key functionality of a digitally programmable analog DUT. And we've seen that XModel integrates seamlessly with all the covered syntax of the SystemVerilog language, including cover groups, cover points, cross coverage, the sample method, user-defined bins, with constraints, and so on. And the speed of XModel, even in simulating a transistor level DUT, makes lengthy iterations quite practical. In the next section, we'll look at our top level block.